Hello, guys, and welcome to the second unit of the year here, Atomic Structure and Quantum Theory. And I'll jump right in here. So, the first section of the unit is regarding the history of the atom. And we've got kind of a unit essential question here that we'll think about throughout the whole unit. And that's how do the properties of subatomic particles determine the different chemical properties displayed by atoms of each element? And then I have kind of a sub question that I really want you to focus in on today, and that's how did scientists determine information about these tiny subatomic particles? Now, we don't know the answer to these yet, but hopefully we can come back at the end of the unit and think about this. So the first thing I did in this unit is I just put up a listing of the oldest elements that we know of that have been discovered, the first anyway, and the year that they were discovered by humans. And as you look at this list, I want you to just think about why did we discover certain elements before we discovered others? And hopefully you guys have a periodic table around and you can kind of look at that. That might help provide some of that information. The first thing I want you guys to think about is, are these elements solids, liquids, or gas? The elements at the top of the list tend to be solids, which is important. The gases didn't really get discovered. We see hydrogen, oxygen, nitrogen, chlorine down near the bottom until about the 1700s. So solid elements tended to be discovered first. The other thing that an element required to be discovered early was just general usefulness, things that people used quite a bit: copper, lead, gold. Some of those things were used for weapons, some were used for pottery, some were used for jewelry or coinage. So those things tended to be discovered sooner than other elements that might not be as useful back at that time. One last thing that's really important for why some elements are discovered earlier and many more aren't discovered until later is reactivity. Elements that don't react are called inert, and those elements are found in their elemental form. And there are many other elements that weren't discovered till much later because they're rarely found just by themselves. They've already reacted with other substances. That'll kind of be something that's important for Unit 3, but that way of thinking about elements I think can help us in this unit as well. So let's start with, how do we really know that the atom exists at all? And we're going to work on a lab, or we may have already done that in class, that goes with this concept. But scientists had to first discover the atom, and believe it or not, that seems like common knowledge to us, but for thousands of years, the atomic theory was not the leading theory. Greek philosophers debated how Earth was composed, and Democritus was the philosopher who supported, or the biggest supporter of the atomic concept, but he didn't really have any evidence to support it. He just kind of argued for it with no experimental evidence. And that's why Dalton gets credit with the atomic theory. He did have some experimental evidence and used some mathematical principles that we'll talk about in class. And he came up with these basic rules, or kind of tenets, of the atomic theory. He says that all matter is composed of tiny, indivisible particles called atoms. Atoms of an element are identical in size, mass, and properties. He also said that atoms of different elements can combine in whole number ratios to form chemical compounds. That's related to the lab I was talking about. And then in chemical reactions, atoms are combined, separated, or rearranged. That's the law of conservation of mass, really, right there. This theory was developed in 1805, so relatively recently. Certainly many elements and atoms had to be discovered by the time that this theory was put together. You'll also notice there are two underlined words: indivisible and mass, and I underlined those words because they were the incorrect parts of his theory. So in 1805, Dalton came up with this theory based on scientific investigation, but some of Dalton's theory had to be altered. I don't like to use the word disproven here because a lot of what Dalton said was correct, and this happens all the time in science where we're more refining theories. One scientist discovers something, a lot of it is really groundbreaking, a few pieces might need to be refined or altered. And the things that we've since altered, atoms are divisible into smaller subatomic particles, and atoms of the same element have identical properties, but they can have different masses. So modern atomic theory has changed those two ideas as we've gathered more information. Now, this isn't in your student notebook, but you are responsible to kind of know this stuff for the quizzes and tests. And I just want to quickly go through a list of scientists who really were critical in gathering information about the atom. It's important to think about the process and how these scientists gathered information. Now, William Crookes, he invented what was called the Crookes tube in 1875, and these were used in early televisions, but they're also going to be used in many important science experiments. And these tubes just allow light to be shined through them or passed through them using electrical current. So it basically converts electrical current into light. And you can see an example here. The Crookes tube was also sometimes called the cathode ray tube. And the cathode ray tube experiment was conducted by J.J. Thomson in 1909. And you can see a design for it in the picture here. There is a voltage supply, and what that's doing is it's pulling electrons off of the anode and bringing them around the wire and replacing them back at the cathode. And this creates a negative charge at the cathode. There's extra electrons over there that are repelling each other. On the other side, the anode becomes very positive. It's attracting those electrons, and then the electrons start to jump across the plate to create a circuit, or to jump across the tube, I should say. Now, what J.J. Thomson did, scientists knew about these tubes and how these rays worked already, but Thomson said, if I put a positive charged plate and a negative charged plate on the sides, I can figure out the charge of whatever's creating that light. So he discovered negative electrons when the fluorescent beam was deflected toward the positive magnet. The electrons had to be negative if they were going towards the positive magnet and away from the negative magnet. This allowed Thomson to create what he called a model of an atom. And he said that the little negative dots, those are the negatively charged particles called electrons. And then he said the rest of the atom is just this kind of sea of positivity, but it's not very strongly positive charge because the negative charges are really concentrated, and the rest of the atom is this kind of positive sea, but it's not very strong. We use the term sea because you think of a solid as a dense physical object, but a liquid, it is a physical object, but it's not as dense. You can drop something and it goes through a liquid, whereas it doesn't go through a solid. So that's kind of why we call it a positive sea, because it's a weakly positive area. Now, we've got a couple other experiments that I want to think about. The next one is the oil drop experiment in 1908. And Robert Millikan, what he did is he sprayed oil droplets into an electrically charged region. And you can see a picture of his experiment down at the bottom. So there's this cover, and you kind of see what looks like a box with the yellow dots in it. Those are the oil droplets. But the experiment itself isn't really taking place until the very bottom, when the droplets end up going into that uniform electric field. And what Millikan did is some very complex math to determine the ratio between the mass and the electrical charge of an electron. So he was able to determine what we call the elementary charge, essentially the charge of the electron. And his work really led to both understanding the charge of the electron and the mass of the electron, which is very, very small. I'm going to just go back quickly to the cathode ray tube experiment. And one thing I wanted to add about this is that Thomson, by adding a little spinning wheel into the tube, he was able to determine that the electron did indeed have some mass because it was able to spin this wheel that can be added into the tube. So that takes us through the Thomson experiment and the oil drop experiment. I want to talk a little bit about another scientist, Eugene Goldstein. Goldstein researched cathode rays and discovered the major visible ray is produced by a negative electron. So Eugene Goldstein discovered that the major ray was caused by a negative charge. He also saw other rays going in the opposite direction, and those were produced by positive ions. Now, this isn't so much a part of the test, so it's just to kind of give you a complete picture here with Goldstein. The next experiment I want to talk about very quickly here is the Rutherford gold foil experiment. And part of me wanted to put this right after the Thomson experiment, but timeline-wise it happens a little later, but it's very closely related to the Thomson experiment. In fact, Ernest Rutherford was a graduate student who worked for J.J. Thomson. Now, if you remember that plum pudding model of the atom, and I'll go back to it here, it looked like this. Keep that in mind as we move over to this animation that shows what Rutherford did. So, Ernest Rutherford did this experiment that you see pictured here. He took a very thin gold foil and he passed some alpha particles through it. Now, what you need to know about these blue particles is these are positively charged particles. And as they come towards these atoms, most of them go right through without deflecting at all. And then some of them you see hitting this screen over here at varying angles, so they've clearly deflected away. Now, when Rutherford did the experiment, he expected to see very few of the particles go straight through, and he expected most of the particles to deflect at kind of small angles. And the thing you'll notice that's very peculiar here is that some of the particles deflect at very wide angles, and the other thing you'll notice is some of the particles are bouncing back. Now, when we go back to Thomson's model of the atom here, and I accidentally started that from the beginning. When we look at Thomson's model of the atom, what would positive particles be bouncing off of that would send them straight backwards? So Rutherford said, this model of the atom must not be correct. And it was very hard for him to do that because he worked with Thomson. So he actually sat on this information for a couple years, really trying to think about it and redo the experiment, looked for different ways, and the only thing he could come to was there must be a positively charged center of the atom. And so we'll go over here. Rutherford proved positive protons are located in the nucleus, and he also, through some math work in the experiment, said the nucleus is almost 2,000 times smaller than the atom. Most of the atom is empty space with these very small electrons moving through it. The nucleus is very, very tiny, but it holds most of the mass of the atom. And this is just kind of an example of the Rutherford model now. We have a positively charged nucleus at the center. The electrons are orbiting, and of course this is not to scale. The nucleus is in reality much smaller. It would be almost impossible to see on this graphic. The electrons would be smaller. The atom is mostly empty space. The textbook uses an example, and it says if you were in a stadium, let's say a football stadium like for the Eagles or the Steelers or Penn State, if you put a football on the middle of the 50-yard line or in the middle of the field, that would be the size of the nucleus. The entire stadium is the atom itself, most of which is empty except for little pin needles that would represent the electrons. That would be to scale of what the Rutherford model looks like. Now, the next scientist I want to talk about is Niels Bohr. Niels Bohr wondered, why didn't electrons just fall into the center of the atom? because of the attraction from protons? And that was a really good question. Um, so Bohr applied quantum mechanics to the atom. And when I say quantum mechanics, that's a really difficult concept. If you go on into advanced chemistry, you'll kind of talk about what that means. But he essentially argues that electrons carry energy and they can never lose it all. So that's why electrons cannot get into the center where they'd be attracted to the protons. But when going back to the word quantum mechanics, it's a really complex mathematical field that basically proves that there are specific values of energy that an electron can have, or any particle can have. If you think about watching like an animated cartoon, if you think about like Disney and Mickey Mouse, back when they used a picture frame and then another picture frame and another picture frame, and you could kind of see the pictures being replaced. You could tell that it wasn't a live video, but it was picture after picture after picture. Well, now we've improved our cameras so much, and we've improved the frames per second so that we're seeing 20 or 30 pictures every second, and they blur together and become an image. And that's what video is. It's just many images quickly repeating themselves. And so the changes look very fluid. That's what's happening here with electrons. The electron can only be either on the first energy level or on the second level. It can never be in between. And then it bumps up to the third energy level, and so forth. So electrons can gain energy moving further away from the nucleus and lose energy moving closer, but they have to be on one of the energy levels. Now, Heisenberg, in 1927, he said that he came up with this uncertainty principle, and it states that it's impossible to know the position and momentum of an electron. You can't know both of those things at the same time. This is a really difficult concept for students to understand, but what it means is that electrons can only be said to be within a region of space which we call an orbital. We can't say exactly where an electron is. So if I go back to the Bohr model at the bottom of this page here, Bohr is showing the electrons following these planetary paths, but electron motion is much more complicated than that, as we'll see in the coming days. I'm going to scroll back. One of the scientists I skipped over a little earlier was Max Planck. And Planck had been working back around the year 1900 to develop this equation, which says that E equals h times nu, which it's a V here, but it should be a Greek letter there. And what that means is that the energy an electron carries is going to equal Planck's constant times a frequency. And so basically what Planck was doing is he was using a specific frequency of light, determining the energy that the particle was carrying, and he kept coming back with this number, the Planck's constant, which was 6.626 times 10 to the negative 34th, and the unit for that is joule seconds. So that takes me to Erwin Schrödinger, and in 1926 what he did was develop a complex equation to calculate the properties for waves. And we're going to talk about whether or not matter is a wave or a particle, what that means, and we'll kind of unpack some of what we learned from what these scientists have all done. The last one here that I want to look at is James Chadwick. He wondered what's holding all of the protons together in the nucleus. And that allowed him to discover the uncharged particle in the atom, the neutron, which provides for the force that holds protons together. Remember that protons should repel each other because they're all positively charged. So we want to kind of figure out what's holding them together. Chadwick did some experiments. They were very complicated. And he was able to discover that the neutron must be present in the nucleus and provide that force. some competing theories at the time, uh, basically, because scientists could start to tell the mass of atoms, they knew that the mass of an atom included more than just the protons. And because electrons were, remember, almost 2,000 times smaller than protons, there had to be some other particle in there. Now, the other leading theory said maybe instead of, let's say an element has a mass of 10. Well, some scientists would have said that had to have 10 protons in it, but if it only had 5 electrons, then that didn't make sense because the charge of the atom was neutral. So if it had 5 electrons and 5 protons, that didn't make sense because the particle, the mass needs to equal 10. And so that's one of the things that got scientists thinking as well, that there must be another particle and it must have mass in the nucleus, and that's the neutron. So I'm going to just go back to our question so we can think about these a little bit more. So how do the properties of subatomic particles determine the different chemical properties displayed by atoms of each element? I don't think we can really answer that yet, but we do know some of the properties of subatomic particles. I've been talking about mass and charge and even location of these particles. And we don't really know the different chemical properties displayed by atoms, but I can tell you that atoms of different elements do behave differently. And I think we can guess that the reason is going to be because of these properties of subatomic particles and the number of subatomic particles in the different types of atoms. Our sub-question here, though, how did scientists determine information about these tiny subatomic particles? Well, scientists clearly conducted experiments. They didn't just guess, but they gathered information and they interpreted their results to form logical conclusions. The other thing I want you to recognize is that the work of scientists largely built off of each other. William Crookes discovered that cathode ray tube, which allowed Thomson's experiments to work. Thomson developed the plum pudding model, but then Millikan and especially Rutherford went back and kind of looked at that and reformatted the model. And other scientists advanced as well. So I think that's where we're going to leave for today, and next time we'll focus in a little bit more on the properties of atoms, the properties of subatomic particles. So you guys will have some assignments to be working on, and I'll see you next time.